Welcome to Aerodynamics of Flight, Part 1. The longitudinal axis of the airplane runs from the tip of the spinner to the tail. The lateral axis runs from wingtip to wingtip, and the vertical axis runs up and down perpendicular to the other two reference lines. Theoretically, all three lines pass through the center of gravity about which movement occurs. The ailerons, located on the outboard portions of the wings, cause the airplane to bank along the longitudinal axis. The elevators allow the airplane to rotate up or down along the lateral axis, increasing and decreasing the angle of attack respectively, and the rudder yaws the airplane to the left or right along the vertical axis. The chord line is a line drawn from the leading edge of the wing to its trailing edge. The vertical component of lift acts perpendicular to the aircraft's flight path through the wing's center of lift. The total lift vector acts perpendicular to the chord line of the wing. Weight opposes lift and acts vertically downward through the airplane's center of gravity. Thrust is the forward force applied to the airplane, increasing its total energy, and generally acts parallel to the longitudinal axis. Drag opposes thrust, thus stealing energy from the airplane, acting rearward, parallel to the relative wind. In steady flight, the sum of all upward forces, not just lift, equals the sum of all downward forces, not just weight, and the sum of all forward forces, not just thrust, equals the sum of all rearward forces, not just drag. For example, in a climb there is a portion of thrust which is directed upward, contributing to lift, while at the same time a portion of weight is directed backwards, contributing to drag. How an airfoil generates lift is complicated, but generally there are two accepted principles contributing to lift. One is Bernoulli's principle, which essentially states fluid which becomes accelerated is associated with a decreased relative pressure. Thus, as air flows over the top of the wing and is accelerated, there is decreased pressure contributing to lift. The other theory contributing to how lift is created is Newton's third law, which basically states for every action there is an equal and opposite reaction. So as the relative wind is deflected from the undersurface of the wing downward, there is an opposite force lifting the wing upward. In this animation, the green line approximates the chord line as the airplane is rotated to a climb attitude. The angle of attack is defined as the angle between the chord line and the oncoming relative wind. The elevator controls the angle of attack. Back pressure increases angle of attack, while forward pressure reduces it. For any airfoil, there is an angle of attack beyond which the wing will not produce enough lift to counteract the aircraft's weight. This angle is referred to as the critical angle of attack. While the elevator changes the angle of attack of the entire wing surface, the aileron can increase the angle of attack on the outboard portion of the wing. Moving an aileron down when the wing is close to the critical angle of attack can cause it to stall as the chord line changes and thus increases the angle of attack. This will become more important in other lectures when we discuss stalls. Coefficient of lift and angle of attack. The coefficient of lift is an experimentally derived value describing the airfoil's lifting characteristics. The graph shows how coefficient of lift and angle of attack are related at a constant airspeed and demonstrating a roughly linear relationship between angle of attack and coefficient of lift. For example, an angle of attack of 6 degrees, the coefficient of lift is approximately 0.5. If we double our angle of attack from 6 degrees to 12 degrees, the coefficient of lift also doubles to 1.0. If we were to triple the angle of attack from 6 degrees to 18 degrees, the coefficient of lift would increase to just below 1.5. Note the relationship towards the higher angles of attack is not perfectly linear. Since most general aviation airplanes don't have angle of attack indicators, we infer our angle of attack by using our airspeed indicator. As we saw in the previous slide, the coefficient of lift varies in an almost linear fashion up to the critical angle of attack. On the other hand, the coefficient of drag changes exponentially. Note how the slope of the curve increases rapidly with angle of attack. As the critical angle of attack is exceeded, lift does not disappear, but rather falls off rapidly while drag continues to increase. The point at which the wing can no longer produce enough lift to counteract the weight of the plane is called the critical angle of attack. There are two types of drag: parasitic, which is intuitive, and induced drag, which is insidious. Induced drag is the unavoidable byproduct of lift and acts parallel and in the same direction as the relative wind. Parasitic drag is composed of several types. Form drag is caused by the frontal area of the airplane's components being exposed to the airstream. Interference drag is caused by the interference of flow between adjacent parts of the airplane, such as intersections of wings and tail sections, fuselage, wing struts, etc. Skin friction is the most difficult to reduce and is secondary to any roughness on the surface of the skin, which can be from microscopic imperfections which cause local turbulence to rivets protruding from the skin. A clean and well-waxed plane can reduce skin friction. Parasitic drag varies directly as the square of the velocity, whereas induced drag varies inversely with velocity squared. The wing's ability to provide lift depends on the speed of the air over the wing, its size and shape, and the density of air it's moving through. In steady, unaccelerated flight, lift and weight should be equal but opposite, since the upward forces and downward forces equal zero. We can therefore substitute the lift in the equation for mass of the aircraft times the gravitational constant. For practical purpose, we can then simplify the equation by removing the gravitational constant, as well as those factors which the pilot cannot control, such as the air density and overall surface of the wing, and are left with a relationship between the mass of the aircraft and the velocity squared, as well as coefficient of lift, or, as we saw before, since coefficient of lift and angle of attack are related, so for practical purposes, the pilot can consider lift to be affected by velocity and angle of attack. During a normal departure climb without obstacles, we pitch the aircraft for a speed which will provide us with the greatest gain in altitude in the shortest amount of time. This is known as Vy. We do this so in the event of an engine failure, we have the most altitude available, giving us the most options. Now, in the circumstance where there are tall objects just beyond the departure end of the runway, Vy may not provide us with enough altitude to clear the obstructions. In this case, Vx, or best angle of climb, would be preferred in order to gain the most altitude over the shortest distance. The L over D max, or lift over drag curve, describes the contributions of parasitic and induced drag on the total drag imposed on an airplane. At the bottom of the curve, we have the least total drag and therefore our best glide speed. Note, this is not the same as best angle or best rate of climb. When we talk about total drag, we are also referring to the thrust required to maintain a specific airspeed. The airspeed which provides us with the best angle of climb is a function of excess thrust. When we look at the thrust available line compared to the thrust required, note the highest thrust is at the lowest airspeed since the propeller is at a high angle of attack. As airspeed increases, the angle of the oncoming relative wind to the propeller decreases, and as a result, the thrust available decreases as well. The speed at which you have the maximum angle of climb is where the difference between the thrust available and the total drag is greatest, that is, Vx. Vx is that speed which will provide us the greatest gain in height over the shortest distance. Whereas Vx is related to excess thrust or force, Vy is related to excess power. To figure out Vy, we begin by drawing a power required curve. Power is the work done per unit time, so we can compute the power required by multiplying the total drag or thrust by your airspeed. Next, we plot a power available curve, which is thrust available multiplied by the airspeed. As we did for computing Vx, we look at the greatest difference between the power available curve and the power required curve to determine Vy, which in this case is roughly 74 knots. Compare this against the best angle of climb, which occurs at about 70 knots. In summary, Vx, or best angle of climb, is that airspeed resulting in the maximum height over the shortest distance and should be used for obstacle clearance. Vy, or best rate of climb, is that airspeed which will result in the maximum height over the shortest time and should be used for normal climb procedures and after obstacles are cleared. Our last section for this tutorial is on left turning tendencies. Generally speaking, left turning tendencies are the byproduct of the engine and its propeller. Beginning with slipstream, we can see how the propeller rotating clockwise, as seen from the rear, creates a spiraling slipstream which tends to yaw the aircraft to the left along the vertical axis, and also a rolling moment to the right along the longitudinal axis. At high RPMs and low forward speeds, the spiraling rotation is very compact and exerts a strong sideward force on the vertical tail surface. The more compact the spiral, the more prominent the force. As the forward speed of the aircraft increases, the spiraling slipstream elongates and becomes less effective. Torque is the result of the engine rotating. On the ground, this causes a left turning tendency due to increased friction on the left wheel from the clockwise rotation of the engine and propeller. Once airborne, the rotation of the propeller causes the plane to roll left along its longitudinal axis. During the takeoff roll, gyroscopic precession is most noticeable in tailwheel airplanes and creates a yawing moment with pitch changes. Conversely, yawing about the vertical axis will cause a pitch moment in both tailwheel and tricycle gear airplanes. Finally, P-factor, or asymmetric propeller loading. P-factor is caused by asymmetric lift produced by the downward moving blade when the airplane is pitched up, and therefore it experiences a larger angle of attack as compared to the propeller blade on the opposite side, which is moving upward. This relative increased lift on the downward moving blade causes the airplane to yaw towards the left. This effect is greatest at Vx and less so at Vy and cruise climb configurations, where the pitch angle is less. Be aware of this tendency, especially at high RPM settings and at high angle of attacks. Notice how the angle of the relative wind due to the forward motion of the airplane changes as the nose is pitched up. Also notice how the downward moving blade has a relatively larger angle of attack compared to the one on the opposite side moving upward. Thanks for joining us today, and remember, fly smart and stay safe.